los jefes no están. ¿Qué hago?
Pues hay Luis y no lo sé. Están con Bafa, que está en la entrevista.
Es Rafael y Fernando. Entonces creo que me puedes decir.
Sí.
Okay, we'll start with the last two talks of the day. Now we'll hear Hans Jockers on moduli spaces of string compactifications from gauge theory correlators.
Thank you very much. Also, thank you very much to the organizers for organizing this wonderful workshop. I'm very thrilled by all these interesting talks, and I'm learning a lot. So today I will be talking some work with my students, Andreas Gerardus and Omi Ninat, in Bonn, on some upcoming work which hopefully comes out the next couple of days. So what's the motivation for this work in the context of this workshop? Well, in general, when we want to study compactifications down to 4 dimensions, we would like to study effective theories, effective supergravity theories, and in particular, ideally, also in order to address phonologically relevant questions, one would ideally like to have control over interactions of these low-energy effective theories. And while there are various scenarios where you can study this question, so one of the oldest is the type 2 compactifications on Calabi-Yau manifolds, on the relevant interactions that arise there come from the moduli spaces of Calabi-Yaus. In the course of this F-theory workshop, we have also, obviously, Calabi-Yau fourfolds, if you want to go to 4 dimensions, play a prominent role. But also the structure and the moduli of Fano threefold bases play an important role, as you have seen in various talks. So I'm personally also interested in this program of constructing G2 manifolds, which also Andreas Braun, I think, talked on Monday about. And also in this case, there is a certain cluing condition. And in order to fulfill this cluing condition, what you have to understand quite well are the moduli spaces of the arising geometries, and in this case, these are particular non-compact Calabi-Yau threefold geometries, so-called asymptotically cylindrical Calabi-Yau threefolds. And it would be nice also in this context to develop tools to actually study these moduli dependencies. Well, unfortunately, I won't have to say too much about this motivation, and I also have to admit that for me, looking at this story that I'm going to tell you today, I also had a different motivation in mind, but nevertheless, let me present this work for you as a tool where you might want to judge whether it's going to be useful or not to maybe address some of these questions listed up there. So what I would like to do is I would like to compute differential operators that capture certain moduli dependencies by correlator techniques. So standard techniques to do so, or very powerful techniques to do so, variation of thought structure techniques, in particular in combination with mirror symmetry. And what I would like to tell you today is some alternative approach, which sometimes turns out to be computationally quite easy to achieve. So what I would like to be looking at are certain correlators in certain 2D gauge theories that I'll review. And I would like to tell you a method how to actually arrive at non-trivial relations among these correlators, and then use these relations actually to derive differential operators that annihilate certain moduli-dependent quantities. Okay, let me get to the first part. So let me get to a brief outline. So I will tell you what 2D gauge theories I have in mind and what correlators we are looking at, how we can get from correlators to differential equations, and I'll discuss some examples, and then I come to my conclusions. So to the 2D gauge theories. So the 2D gauge theories I have in mind, they're also known as these gauge linear sigma models that have been introduced quite some time ago now. So but what I'm particularly interested in this context is that we do not just look at abelian gauge groups, but that we also allow for non-abelian gauge group factors, so that G1 through Gn are in general some semi-simple Lie groups. And even more generally, you could also take this gauge group and mod out by some discrete subgroup, but let me not talk about such details here. And associated to this gauge group in these 2,2 theories, we have a vector multiplet. In addition, what we would also like to specify are the charged matter chiral multiplets. And then in this context, what we have is a gauge linear sigma model Lagrangian, which in superspace takes this typical form. We have a kinetic term for the twisted chiral multiplets, and we have a kinetic term for the matter multiplets, and then we have some interaction on moduli term dependent terms. We have a superpotential interaction in general, which depends on some moduli. And we also have, for the U1 factors, we can write down a term which you might not be so familiar with from four-dimensional theories with four supercharges are these complexified Bialopoulos terms, which couple linearly to these twisted chiral multiplets. And then, so the semi-classically, the parameter dependence is now these coefficients, which we have in these superpotentials, and these coefficients in front of these Bialopoulos parameters. So that's one ingredient, which is well known. So the other ingredient that is more recent is that in these gauge theories, we can actually very straightforwardly and efficiently compute correlators by correlation techniques. And this has been worked out explicitly in these two papers, which appeared about the same time in 2015. And the idea is the following. We are interested in a particular kind of correlators, namely the so-called A-twisted correlators. And the idea is the following. So we want to study these gauge theories on a curved space, namely on a sphere. And in particular, for projecting on these A-twisted correlators, we also allow for a certain off-shell supergravity background of the following type. So on the two-sphere, we have a killing vector field K mu, and then the two-dimensional gravity multiplet consists of two graviphotons, and one of them we give an expectation value which is proportional to this killing vector field, and it comes as a proportionality constant. Now in this context, then you can use localization techniques to actually compute certain correlators, namely correlators of this type. They holomorphically depend on two quantities, namely at these exponentiated Bialopoulos parameters, or the complexified version of these, and on this parameter epsilon. And the kind of correlators you want to compute is you want to compute a number of the insertions at the fixed points with respect to this action of the killing vector field. And so we have insertions of the sigma field, which is the lowest component of the twisted multiplet at the north pole and the south pole of this two-sphere. And then these correlators can be computed explicitly as a certain sum over certain vortex actors, where we have now here contributions from one loop determinants that you have to compute in this localization recipe. So what makes this thing for me interesting is that to these gauge theories we can actually also associate geometry, and the geometry is the target space geometry, and again semi-classically the scalar potential, or minimizing the scalar potential, tells you what kind of geometry you get. And the kind of geometries you get are complete intersections, typically in symplectic reductions of these spaces, or more algebraically, these are GIT quotients, which we get from the corresponding complexified reductive groups. So we've heard also this morning by Anders a similar situation where when he talked about this resolution, it left kind of the toric regime, and there was, if I understood correctly, also a more general setup where you could describe it still in terms of GIT quotients. So one thing that I would like to advocate is that these gauge theta sigma models, although they have been used in the past, a tool to describe physically toric varieties, they can actually also be used to describe more general GIT quotients, as we also will do in this talk. So this brings me to this part. If we restrict to abelian gauge groups, we actually describe complete intersection toric varieties, so we're doing toric geometry. For non-abelian gauge groups, we would describe non-complete intersections and projective varieties, which, for instance, could be complete intersection in Crossmanians, but also complete intersection in more general flag varieties or GIT quotients. I should also say there is another interesting story here that we actually study in this context. I'm not going to touch this here. So you have certain strong coupling phenomena. So this is a 2D version of Siebeck dualities, sometimes also called Hoare dualities, where you can actually look at certain quantities, and the correlators are among them, where you can actually compute certain quantities in these strongly coupled regimes. So let me point out one very basic property of these correlators that we're computing, namely there is a certain selection rule involved. And this comes from the U1R axial anomaly, which is typically present in these models. And it essentially tells us that these correlators only get contributions from monomials which fulfill this equation, namely the dimension of the target space plus the power of this variable epsilon, which was related to this proportionality constant with respect to the killing vector field, times the first Chern class of that target space times the power of the Q variable has to equal the number of insertions to give us something non-vanishing. Okay, so if you take this selection rule into account, then and apply it to some let's say extreme cases, namely the Calabi-Yau target spaces. This is something which has probably been most studied in a string context. Then these kappa and m, as a consequence of this selection, will actually, together with some further considerations where singularities in the space, in this moduli space of these 2D gauge theories, results that these kappa and m are actually rational functions in Q. For Fano target spaces, you can argue that the correlators have to be finite in the limit Q goes to 0, so that then the selection rule tells you that the K and M are actually polynomials in Q. And the other extreme case is if you have an ample canonical bundle target space, then actually Q inverse to 0 has to be well defined, so K and M are polynomials in Q inverse. So the reason I'm mentioning this, so for these particular geometries, this already tells you that these correlators are actually very special, namely they're either rational functions in extreme cases or polynomials. So you actually might expect that there are, it's not so surprising what I'm going to tell you next, that there might be relations relating these different correlators, and this is what we're going to exploit. So what is the idea of this talk? So I've told you that we have these gauge theories. Via symplectic reduction or GIT quotients, we can relate to gauge theories actually Kähler target spaces. We can study the parameter dependence in these gauge theories. I've just mentioned the Violopoulos terms, but another thing you can turn on are twisted masses. I won't do this in this talk, but if you include twisted masses, you also include this word equivariant. In any event, by studying these Violopoulos parameters, what we can actually study are quantum cohomologies on these spaces. And what I would like to tell you today is that if you compute these A-twisted correlators, there's actually a nice correspondence between quantities in these cohomology groups and what these correlators mean. Okay, so let me now get to the point where we study correlator relations and resulting differential equations. So here's what we want to do. We want to take, well, there are two kinds of relations actually that we mainly focus on. It's so-called South Pole and North Pole correlator relations. Let me focus on the South Pole correlator relations. So this is essentially saying that if you take a certain linear combination, a finite linear combination of such correlators, we are looking for coefficient functions which depend on Q and epsilon such that they add up to 0. And it turns out that there are such relations. And these relations actually come from a certain constraint. Namely, they arise as functions, they arise as from certain polynomials alpha p, which enter in this particular way here. And the GPs, which are actually the defining function or the defining functions for these alpha p's, they're just rational functions which you can immediately off from the two-dimensional spectrum. And they're very easy to write down. I'm not doing it here because I would need to introduce a bit more notation, but you can believe me that these functions are actually quite simple and can be readily written down from the spectrum. So the importance is of these relations, so this is why we call them South Pole correlator relations, that they actually do not just hold for a particular set of correlators, but they hold independently of the number of insertions on at the North Pole. So in other words, they only depend on the number of South Pole insertions. And the other thing that you should note, if you find one alpha, you certainly can find another alpha by uniformly multiplying all the alphas as a polynomial. But nevertheless, it enters in a somewhat non-trivial fashion in this relation because there's this shift by p. But the upshot is that, well, not in principle, you can in practice very easily determine these relations from the GPs. And if you have more complicated example, you can use Gröbner-based techniques to actually write down all the generators which fulfill these relations. Okay, so I mentioned already that there is this funny shift in P. This allows us to actually give an operator interpretation, and this brings us to the differential equations of these correlator relations. So let's say we assign to each value of Q a certain Hilbert space H of Q, and let's also assume that we have a ground state omega Q for each Q. Then, by introducing by enhancing these insertions at the south pole and these Q's to operators which fulfill this commutation relation, and this commutation relation is precisely designed in such a way that it reflects this shift that I mentioned before in the alphas, that as you multiply the alphas as a polynomial, it gives you a new relation, that this is very naturally incorporated in this, if you want, this non-commutative ring construction, or if you want in this operator language, then these relations that we had on the previous slide come to the statement that these operator value quantities actually annihilate this particular ground state that we have in that theory. And if we now introduce for this commutation relation a particular representation in terms of differentials, maybe in terms of logarithmic differentials, you immediately get from the correlator relations to differential operators that annihilate this ground state. And I should say, there is, by Hoy and Waffa in 2002, and this paper on mirror symmetry, there is a proposal at the end how one can actually also, in this more general setting of GIT quotients and Grassmannian flag manifolds, how one can actually also derive from certain integrals periods. It's the same kind of, so, and then you can also ask what kind of relations do these periods obey, and we recover the same kind of, for these examples that are discussed in this paper, we recover the same kind of relations that we construct here from the correlators. Or said it differently, in the maybe most studied case, namely in the conformal case, these become the Picard-Fuchs operators of the periods of the corresponding Calabi-Yau manifolds, or the periods of the moduli spaces associated to these Calabi-Yau manifolds. But actually, this picture holds more generally, namely these correlator relations actually become differential operators describing quantum periods. It's not just for Calabi-Yaus, but also for other geometries. And this can be argued for by actually working out the correspondence, what these relations actually mean, and these correlators actually mean geometrically. And I'll give you the result here. So the basic property is that one can identify them or make a connection to the given tau I function. So the given tau I function, translated already a bit in the language as we use it here, it's a function which also depends on this variable q, and this parameter epsilon, and it takes value in the even cohomology of this target space X. So from a math point of view, what this I function encodes essentially are the quantum periods or the quantum cohomology ring of X. So from the gauge theory, what it encodes is essentially certain operator products of these scalar fields. And one can actually ask, I mean, how can we translate these correlators in terms of the I function? And for very specific geometries, this correspondence has actually been proven. Like I forgot the details, but I think essentially for projective spaces and maybe for some Grassmannians. But what we observed that this actually holds more generally, namely if there's a certain bilinear pairing of these I functions, and these insertion and M then just correspond to taking certain differentials with respect to this logarithmic differentials with respect to this Q variable. So now we can take one of these correlator relations and actually essentially plug it into this relation, into our correlator relation. And what we find is that these differential operators are nothing else but the operators which annihilate the given tau I function. So these operators, in a sense, they encode or the solutions to these operators, they encode the quantum periods more generally, or the quantum cohomologying of these spaces. Let me actually turn the logic a bit around. One other thing that you can do with these correlators is ask the following question. I mean, are there universal differential operators that you can assign to certain geometries? And the idea is to solve these relations that we have in terms of the correlation functions kappa and m. And simple examples are that, for instance, if the class of geometries which you might want to consider are Picard-Fuchs operators of Calabi-Yau folds, namely of elliptic curves. And it turns out that from this correlator approach, if you want to derive this Picard-Fuchs operator, the only thing that you have to do is you have to compute the kappa 0,1 and the kappa 1,2 correlators, and then you can always write down the corresponding Picard-Fuchs operators. Another example would be, for instance, Picard-Fuchs operators of Calabi-Yau folds with a single Kähler modulus. For these types of geometries, you also can universally write down a corresponding Picard-Fuchs operator, which now depends on a bunch of correlators that you need to compute. And actually, there are also still some relations among these algebraic differential relations among these correlators here. So it turns out that you only need 3 correlators to compute in order to arrive at the Picard-Fuchs operator for Calabi-Yau folds with 1 modulus. This actually fits nicely in the classification of 1-parameter Picard-Fuchs operators for Calabi-Yau fold, as has been proposed by Almqvist and collaborators. And actually, they also give conditions for Picard-Fuchs operators in order to be Picard-Fuchs operators for Calabi-Yau fold geometries. They give conditions on these conditions, and these conditions we exactly reproduce in our context from the correlation perspective here as well. So let me give you actually, at the end, a few examples which will illustrate a bit how we can use that technology. So, for instance, if you want to discuss the final variety Grassmann 2-4, you will see momentarily why I picked this particular one and not another one. You can realize that the GIT quotient very simply by this falling spectrum. Since it's 2 planes in a 4-dimensional space, the corresponding gauge group would be U2. And then, in order to realize this complex 4-dimensional vector space where we look at 2 planes in it, we would look at 4 chiral multiplets in the fundamental representation, namely in the 2 of U2. Which has a diagonal U1 charge of +1. Well, the twisted masses, for the purpose of this talk, we set to 0 anyways. And then we can derive, we can compute resulting from the spectrum the correlator relations, and one directly finds one particular relation, which again is a relation that you would also find if you take a look at the corresponding integrals in the Hori-Waffa description of these Grassmannians. And if you stare at this operator, you might notice that this is actually the Picard-Fuchs operator, which is associated to the projective space P5 and the degree 2 hypersurface. And this is actually not a coincidence, and this is why I also have chosen this particular Lagrangian, because we can easily compare, because the Grassmann 2-4 actually happens to be identified with a certain degree 2 hypersurface in P5. But we can actually go a bit further and more systematically in this non-abelian context actually study the kind of relations that we get. And there is not just a dictionary about the gauge linear sigma model and the geometry, but there's also the dictionary how I would associate cohomology elements in the geometry with these twisted chiral multiplets. And the dictionary is the following, that the trace of sigma to the R for these UN gauge theories you would associate with the Newton polynomials NR. And the Newton polynomials, These are generators of the, at least of a queue of the Schur functions, and the Schur functions in turn, they give rise to the Schubert cycles, namely the cohomology elements of this corresponding Grassmannians. Well, we also find in this, well, translated already in this language, two more relations of the following type. And this fits nicely with a result, a genus, well, restricted to genus 0 of the buffer interligator formula for the quantum cohomology ring of these Grassmannians, where it's actually shown that these classical relations are deformed by this addition of Q. And also in some math work by Sibel and Tian, this has been shown in a more general setting that if you have a classical cohomology ring in the context of a GIT quotient, under what circumstances and how you have to deform it to actually get the quantum cohomology product. And these kind of structures we also recover here from the correlator perspective. So just to illustrate at the end the second approach, I would like to point out another example of a Calabi-Yau threefold. So this is a Calabi-Yau threefold which is not of the complete intersection type in the toric variety, and it's probably one of the benchmark Calabi-Yau threefold which is of this non-complete intersection type. I mean, this is the analog of the quintic for the toric cases in a sense, because it's one of the simplest. And this has been studied by Rodlin, that's why it's known the Rodlin Calabi-Yau. Anyway, there's also related a spectrum to that, and at least one phase of it you can realize as a complete intersection in a Grassmannian 2-7 in this case. And if you actually have worked out by variation of hot structure technique how to derive this Picard-Fuchs operator, I can tell you it's quite painful. But from this correlator technique, all you need to do is you need to compute these three correlators and plug it in a general formula, and indeed you reproduce the Picard-Fuchs operator that is known in this case for the Rodlin case. Maybe I should say I didn't do this computation, so the graduate students do, so maybe they wouldn't agree with me that this computation is so much easier, but at least it can be done. So let me maybe come to the conclusion and some outlook. So what I've tried to show you that actually these two-dimensional gauge theory techniques are actually very powerful, not just to engineer more general geometries such as GIT quotients, and as we have heard also this morning, that these kind of geometries actually also play a role in the F-theory context, but actually that you can even do computations on these geometries using gauge theory techniques. And actually, these are computational techniques where you don't need to employ methods of mirror symmetry. So in particular, well, I mean, if the geometries are toric, we know very well how to do computations. But if it goes beyond toric, I would just tell you that this is an additional tool. And maybe another thing that I wanted to take a look at, but I haven't done so. So Almquist et al., they look at this classification of Picard-Fuchs operators, and they get certain conditions on the coefficients, whether one can actually apply a similar logic to other geometries, which may or may not be interesting in the F-theory context. So in particular, what I have in mind, Calabi-Yau fourfold geometries that are elliptically fibered with a low number of Kähler moduli, that you still can deal with the problem, or Farnow threefolds, which play the bass, and F-theory, M-theory compactification. So maybe let me stop here.
So I just wanted to ask if you also applied it to multimodular cases, and if it is still computationally feasible even for example, a 5 or 6 modular case, because even for toric cases it can become almost, I mean, it's hard to obtain the Picard-Fuchs system.
That depends a bit what computation you're looking for. So what we've also done, we have, for instance, worked out what is the general form of the Picard-Fuchs operator in the 2 moduli cases, where you have 1 degree 2 and 1 degree 3 operator. in terms of correlators. These formulas are already quite intense. So if you want to work out similar formulas for let's say, order of 5 and 6 moduli, indeed this would be quite complicated, in particular because for 2 moduli there's still a unique answer that you should expect a degree 2 and a degree 3 operator. But if you have more moduli, there will be actually several subcases. But the hope might be that if you take into account additional structures, such that elliptic vibration, that maybe the structure even simplifies further. And I also have to admit that we haven't studied in detail these algebraic geometric relations that you get from these more complicated cases with more moduli.
What about different choices of gauge groups for the GLSM? Has that been explored at all? So, for example, the correlators, are they known how to calculate for? Instead of, you took mostly U2 for the case different from U1, but we could imagine taking other gauge groups.
Yes, you can think of. So the reason I took SU2 because well, the non-abelian part it's rank 1. So if you go to higher rank gauge groups, in principle, it's doable. But the residue integrals that you also have to, I mean, if you want, depending on again what computation you want to do. If you want to explicitly compute correlators, you also have to do higher dimensional residues, and that can get complicated. If you're just after this differential relations, you can do that easily for higher rank gauge groups as well. However, there's a bit of a problem if you want to extract Picard-Fuchs kind of operators. You would like to eliminate all these higher traces operators, which, for instance, you can do with a Cribno basis computation as well. But if the rank of the gauge group gets too high, that also seems to be computational too expensive to carry out in practice.
I just want to make a small comment that the alternative computational methods have been shown to be equivalent to mirror symmetry.
You're referring to your work of these periods with Kentaro-Hori, or?
Yes, they are equivalent to what they
yes. So we actually, for some of the cases, we did compute. We did.
No,
check.
the general statement I'm saying. It's not generally they're equivalent. Not specific cases. General statement.
Okay, so maybe we can discuss afterwards. Yeah.
Maybe I missed it, but which representations can you have of fields when you have the gauge group U2? Or is it always
sorry, where's the question?
Sorry? Hi.
Oh, okay, so yes, thank you.
Right.
So say again.
So for the chiral fields, what representations can you treat on a GLSM? The representations of the
Well, in principle, no, you can do any representation. I mean, yes. I mean, there's no restriction on the representation you can treat.
Introducing boundaries on the GLSM or branes on the target space, is that within reach at all? Or?
Okay, so this is actually a very interesting question. So what you can also do is, you can, I mean, here we did this 8 twisted correlators on the sphere. What you can also do is you do the 8 twisted correlators not on the sphere but on the disk. And then depending what boundary condition you would choose, you would actually pick a particular linear combinations of periods. That's a computation you can do. And actually, I'm currently looking at this in a slightly different context, not in 2 dimensions, but in 3 dimensions. And there's an interesting story there. Yes, I would say. Yeah.
Okay, so while we're waiting for the next speaker, just a very quick announcement regarding